In this video, we're going to be looking at the final law for this lesson, and it's called the combined gas law. So let's go ahead and take a look at that. In the previous laws that we saw, we were basically just changing one variable at a time. We're comparing two variables to each other, looking at the relationship. So for example, in Gay-Lussac's law, we saw that temperature and pressure are directly proportional, and if we change temperature, pressure changes. But we were keeping something else constant. We're keeping the volume constant, and also the amount of gas present. So as long as the volume and amount of gas present were constant, then we can take a look at temperature and pressure and see the relationship. So one thing is constant, and we're only changing essentially, or two things are constant here, volume and amount, and then we're only changing one thing, either temperature or pressure. We're just comparing those two. So if we change temperature, pressure changes. In the other law over here, if we go back up to Boyle's law, what was constant was the temperature and the amount of gas, so how many particles of gas there are. But what we're changing were either the volume or the pressure. We're looking at the relationship between volume and pressure. So if we change volume, what happens to pressure? If we change pressure, what happens to volume? But basically, only one thing is changing there at a time. Everything else is constant. And then for our first law we saw, for Charles' law, we saw, well, what happens if we change temperature? How does it affect volume? Or what if we change volume? How does that affect temperature? So on and so forth. But what was important is that the pressure is constant, so that didn't change, and that the amount of gas there was constant as well. So basically, either temperature is changing or volume is changing, but nothing else. So other things are held constant. Sometimes you might have situations where you might have a change in, let's say, the temperature and the pressure, and you want to see the effect on the volume. So sometimes you might have more than one variable changing at the same time. We're still not going to change the amount of gas, that's going to stay constant, but we can change more than one of the other variables we saw. We can change pressure, temperature, volume, more than one of these at a time. So maybe two of them, and you can see the effect on the other. And so to do that, we just combine all the three laws together. We get what's called the combined gas law. And to write that out as a relationship, we say that the pressure is going to be proportional to the temperature over the volume. So this kind of comes from the idea that we saw, for example, pressure is proportional to 1 over V, but we also saw that pressure was proportional to temperature. And so we just kind of combined these together to give you, well, that there. And so the combined gas law relationship is literally a combination of all the gas laws you saw. So we saw P1 V1 is equal to P2 V2. We saw that your V1 T1 is equal to V2 over T2. And we saw that your uh, P1 over T1 is equal to P2 over T2. So we saw all these relationships, and we can write this out as one combined law, which is P1 V1 is equal to P2 V2 over T1 here over T2 over here. And all the variables mean the same thing: initial pressure, initial volume, initial temperature, final pressure, final volume, final temperature. Temperature still needs to be in Kelvin, and your pressure and volume can be any unit as long as you are consistent on both sides. And you can rearrange this equation to find a whole bunch of stuff. Actually, instead of memorizing all these three here, you can simply memorize um, your combined gas law, and then just get all the other ones from your combined gas law. So if you're only dealing with a problem where you're only changing, let's say, pressure and you want to see the effect of volume, just ignore the temperatures. If you're dealing with a problem where you're changing pressure or temperature and you want to see the effect on pressure, but volume's constant, just take away the volumes, and you have your P1 over T1 is equal to P2 over T2. If you're dealing with a question where you change your temperature and you want to see the effect on volume, well, and pressure is the same, well, cancel out the pressures, and you have V1 over T1 is equal to V2 over T2. So if you remember the combined gas law, you can remember all your other gas laws rather than having to memorize every single one of them like that. So let's take a look at a few sample problems where we might have to use a combined gas law. So I'm going to write out some given information. I find that whenever you write stuff out, it's just going to make the question a little bit easier. We have a small balloon that has a volume initially of 275 milliliters. So that's my initial volume there, at a temperature of 25 degrees Celsius. So 25.0 degrees Celsius, which is plus 273.15, 298 0.15 Kelvin. So we have to make sure we write that as Kelvin when it comes to these type of questions here. Now, our next part over here is we have a pressure, or we are also told the pressure, P1, is equal to 350 kPa. So these are all the initial conditions. And then we're told that we want to figure out what a new volume would be if we change the temperature. We make it so T1 goes to T2 and becomes 10 degrees Celsius. So that's plus 273.15 is equal to 283.15 Kelvin. So we have reduced our temperature, which would reduce the volume. But before we jump ahead of the game here, our pressure was also changed. We also we reduced the pressure. And usually when you reduce pressure, that increases volume. So we have something that decreases volume, something that increases volume here. So we're going to have to use our combined gas law to figure out what our new volume is. And so, again, the reason that we have to use the combined gas law here is because we're changing more than one thing. We're changing the temperature and the pressure. We're not just only changing temperature. We're not just only changing pressure. So our unknown is our V2. And so our equation, this is one where we're changing several things. So our pressure is proportional to the volume over the temperature. All right, let me just write that the other way around. Sorry. Our volume is proportional to the pressure, or to the temperature over pressure. There you go. I get it eventually. So actually, I think I had that right the first time. So let me go back and erase that. So I was just writing out that volume is proportional to, I was just combining it the other way around, but it works this way as well. But I'm going to keep it consistent with what I wrote up there. So pressure is proportional to the temperature over the volume. So proportional to temperature, but proportional to inverse of volume. So inversely proportional to volume, in other words. So what we're going to do is we're going to write out our P1 V1 is equal to our P2 V2 over here over T1 over T2 over here. And we're going to go ahead and plug in our information. So we have our P1, V1, and T1. So we're going to have 350 kPa times our V1, which is 275 milliliters, over our T1, which is 298.15 Kelvin, is equal to our, so V2, we don't know what that is, times our P2, which is 101 kPa, over the T2, which is 283.15 Kelvin. And so we want to solve for V2 by basically isolating. So sending this to the other side to become a division and sending this to the other side to become a multiplication. So we're going to have our V2 is equal to 350 kPa times 275 milliliters times 283.15 Kelvin over the 298.15 Kelvin times 101 kPa. And so we can see if we can cross everything out here. So Kelvin cancels out, kPa cancels out, and we're left with milliliters in the end there. And that would make sense because that's what our volume should be. And so let's do our 350 times 275 times 283.15 divided by 298.15 divided by 101, and we get 905 0.0261265 milliliters. And it looks like we have 2 sig figs as our smallest number of sig figs. So we can round up because we have 5 there and digits after. So this is going to be a therefore statement. So therefore, our new volume is going to be 910, approximately 910 milliliters. And so even though we decreased our temperature, which would decrease the volume, we decreased our pressure, which had the effect of increasing the volume even more. So we actually decreased our pressure more than we decreased our temperature there. And so as a result, our volume increased from 275 mils to 910 mils. Let's go ahead and try another sample problem here. So we have a sample of CO2. It occupies a volume of 25 mils. So let me write that out first. So we have a volume of 25 mils. V1 is equal to 25.0, no, not milliliters, liters, sorry. And the pressure at that point is 125 kPa. And our temperature at that point is 25 degrees Celsius plus 273, 298.15 Kelvin. That's our T1. And we want to figure out what the new volume is once we get to STP. So STP is one of those conditions you need to memorize. STP means that your pressure, your new pressure, is going to be 101.325 kPa. And your new temperature is going to be 273.15 Kelvin. So this is T1 here. This is T2 over here. So what we've done is we've decreased pressure and we've decreased temperature. If we decrease temperature, volume should go down, but we've decreased pressure, so that should make it go up. So the point is that we're trying to make here is that we've changed two things, pressure and temperature. We didn't just change one. So this is going to be a situation where we're going to need our combined gas law. So we're looking for the V2, and we're going to need a combined gas law. We're going to need our gas law that we saw up here, where we have a proportionality that can be written as our pressure is proportional to the temperature over the volume. And so we have our equation is going to be P1 V1 over T1 is equal to P2 V2 over T2. And what I'm going to do is I'm actually going to solve for V2 even before I plug everything in. So if I want to solve for V2, I'm basically sending this down here and this up here. And so my V2 is going to be P1 V1 T2 over T1 P2. And so that's going to be equal to our pressure 1, which is 125 kPa, times our volume 1, which is 25.0 liters, times our T2, which is 273.15 Kelvin, and that's because it's STP, over our T1, which was 298.15 Kelvin, times our P2 there, which is 101.325 kilopascals. We can cross out kilopascals, cross out the Kelvin, and we're left with liters, which is what we want because we want a volume there. So we got 125 times 25 times 273.15 divided by 298.15 divided by 101.325, and we get 28.25529.204 liters. And so for our therefore statement, we're going to, so this is solve and substitute, we're going to write, therefore, the new volume, V2, is approximately, and we need how many sig figs here? Looks like 2 sig figs is the smallest number of sig figs that we have there. So we can round down to approximately 28 liters. And so our volume actually increased because, yes, we decreased the temperature, which would decrease our volume, but we also decreased the pressure. And when you decrease the pressure, that increases your volume. So that overcame the decrease in temperature at the same time. So we have our volume is equal to 28 liters in that situation there. And so now we've seen all the different laws. We saw laws where we just manipulate one variable at a time and compare it to another parameter, like let's say manipulate temperature and see how it affects volume, but we keep everything else constant, like pressure and amount of particles. In combined gas law, we can change two things at once, and that's why we have to use this combined equation as opposed to just a single equation over here. And you can manipulate that combined equation to find a variety of different variables there.